Hello everyone, welcome to this first calculus content video. So in this first video, I would like to give a very quick introduction of where we're going and what we're covering in the course. And then we'll talk about the tangent problem, which is the problem of finding the equation of a tangent line to a curve at a point. And this will give us motivation for studying limits, which is going to be one of the first topics that we look at in the course. Okay, so what are we going to talk about? Well, in this course, surprise, surprise, we're going to talk about calculus. So calculus is a study of change and accumulation. So by change, I mean rates of change. And there are lots of different rates of change you might be interested in. For instance, if you're in a car driving down the freeway, you will probably be very interested in your speed because you don't want to get a speeding ticket. But there are also, many other different types of change that you're interested in. And so this will be differential calculus. And then the other half of calculus, which is integral calculus, is looking at accumulations. So for instance, if you know how a population is changing, then you might be interested in 10 years' time, what the population would be, like these types of problems. And they are connected by something called the fundamental theorem of calculus, which relates differential calculus finding rates of change and integral calculus looking at accumulation. Okay, so calculus was invented or discovered, depending on your philosophy, how you feel about things, independently by Isaac Newton and Gottfried Leibniz. And why do I say independently in quotation marks? Well, Isaac Newton claimed that he discovered it first, he just didn't publish his ideas. Whereas Leibniz wrote a paper much later, but he actually published his ideas. So if you know anything about academics and academia, you know publishing and papers are very important and people get very excited about it. So you can see that there was some contention there. And this is a reason that we're going to have different notation in calculus that mean the same thing because one of them came from Newton and one of them came from Leibniz. Anyway, that's all I'm going to say right now, but if you're interested in that, do have a look on Wikipedia for more about that argument. Okay, so what are our topics? So we're going to start off by talking about limits. Then we're going to look at differentiation, which is kind of one of the two halves of calculus of finding rates of change. So we'll look at what it means, how they're defined, how we calculate derivatives, that kind of thing. Look at some applications, both to mathematics, for instance, finding maximum and minimal functions, and to outside of mathematics, for instance, optimization problems. Then we're going to talk about integration, which is the other half of calculus, so finding areas and looking at accumulation. So how do we define it, what it means, how do we compute those types of things, and so on. Then we're going to look at the fundamental theorem of calculus, which is really important and connects the two halves. It's both useful in terms of understanding and is really useful in computation. So that's going to help us a lot. And then we'll look at some applications of integration, for instance, finding areas, finding volumes, those types of things. Okay, so what are limits? So we're going to define them properly in the next section, but for now, let's just give an idea. So calculus relies on the idea of limits, and limits study what happens to an output of some calculation as an input approaches some number, but is not necessarily equal to that number. And it sounds kind of vague because there are many different examples of limits and they arise in many different circumstances. So if it's something very general, then the best I can do is give a kind of a vague description for the moment. So what do I mean by this? Well, as a very simple example, if I think of f of x equals x squared, and I let x get close to 2, then x squared would get close to 4. Okay, and in this case, it's very simple. I could just say x equals 2, then x squared will be 4. So it sounds like I could just plug in. I don't have to do this whole drawn out process. But there are lots of examples where we have to look at what happens as our input approaches some number but is not equal to it. For instance, if making it equal would lead us to divide by 0 or something like that, that would be a bad idea. Okay, so we'll see some examples in this video and in the next video that show why we have to study limits. Okay, so here are the two examples. So the first example is going to be the tangent problem. So it's the problem of finding the tangent line to a curve at a point. So let's remember that a tangent line to a curve C at a point P has two properties. So it's specified by the following two properties. One, it should pass through the point P. And secondly, it should have the same direction as the curve at that point. So here is a picture. So there is a blue curve and there is a point highlighted on the blue curve. And then we can see that the orange line is a tangent line because it passes through the point we're interested in. And somehow at the point we're interested in also has the same direction as the curve. If we slide the line along to the curve, they somehow have the same direction. So this was great in that we already had a picture of the blue curve, and we can just kind of eyeball it, maybe draw it with a ruler. We can see how to do it. But what if we just had, say, the equation of a curve? We didn't have the graph of a curve, or if the tangent line was something more complicated. So how do we systematically go about finding the tangent line to a curve? Oh, and before I go into that, let me briefly point out that tangent lines might intersect the curve in more than one place. For instance, here the orange curve is a tangent line to the blue curve at the point we're interested in, but it intersects it also way over here on the left. So there's a kind of common mistake that people seem to think that tangent lines only touch a curve at one point. If you look further away from the point where it's tangent, then it might intersect in more places. Okay, but systematically, how do we find the tangent line to a curve at a point? So remember, there are different ways to specify lines if you want to find the equation of a line. One of them is point-slope form. So if we know a point on the line and we know the slope of the line, then we can use point-slope form y minus y1 equals mx minus x1 to write down the equation of the line. So since we're interested in finding the tangent at a point P that is normally given to us, well, that gives us a point on the line for free, right? The tangent line passes through P. So the only thing we have to do is come up with what is the slope of the tangent line. Okay, and that is slightly harder. So we break it into 2 steps. So first, instead of directly writing down the slope of the tangent line, which we can't do, we look at a nearby point Q, which is on the curve and close to P. So we pick another point Q, which is on the curve. And then we look at the so-called secant line PQ. And all secant line means is it's just the line joining 2 points. So we look at the line joining P to Q. Okay, and we can write down an equation for that line. We can draw that line. It's a known line. And instead, we find the slope of that line. So the slope MPQ of the secant line from P to Q. So how do we do that? Well, P is a point we know. Q is a point we chose. We have coordinates for those 2 points. So if we want to find the slope of the line joining them, we just do change in y divided by change in x. And that will give us the slope of the secant line PQ. Okay, so if we pick different points Q, we can calculate this MPQ for different Q. And we'll see some examples how to do that on the next slide. But then that wasn't the problem, right? The problem was to find the slope of the tangent line. So how do we do that? Well, as Q gets closer and closer to P, the slopes of these secant lines PQ get closer and closer to the slope of the real tangent line. So we just look at these slopes MPQ, we see what kind of number they approach. Hopefully they approach something. And we pick out that number. We say that number is the limit of the MPQ that we calculated. And okay, we have this notation that we'll talk more about later. The limit as Q gets closer and closer to P of MPQ equals M. So the limit of the slopes of the secant lines is the slope of the tangent line. Okay, and here is the idea in a picture. So we have a purple curve. Sorry, there are lots of things on top of each other, so it might be hard to see, but there is a purple curve. And we want to find the tangent line. The tangent line is in green, so it goes through the point we're interested in, and it somehow has the same direction as the curve. But how would we calculate that? How would we find its equation if we didn't know it, for instance? Well, we pick a nearby point Q on the curve. So the red point is the place we're finding the tangent line, that's known. We pick a nearby point Q on the curve, which is up here, and then we look at the line joining P to Q, which is the dotted line. Okay, and that's something we can calculate. We can find the slope of that dotted line. So the dotted line is PQ. We find its slope. We look at what happens as this Q gets closer and closer on the curve. And if we plot more and more lines as this Q gets closer and closer to the red point P, then the line will get closer and closer to the green line, which is going to be our tangent line. Okay, so the takeaway of this is, how do we find the tangent line? Well, we know the place that we're finding the tangent line, so that gives us a point on the line. We have to find the slope of the tangent line. To find the slope of the tangent line, we first find the slopes of lines PQ, where Q is a point on the curve and close to P. And then as Q gets closer and closer to P, those numbers get closer and closer to the slope of the tangent line. So let's see an example where we actually do this. So here's a problem. Find the equation of the tangent line to y equals x squared at the point P, which is 2, 4. So remember, we have to go through the steps. So firstly, we know the tangent line goes through P, which is 2, 4. So that gives us a point on the tangent line. And then the problem is to find the slope of the tangent line. So we said there were 2 steps to do that. We should look at a nearby point on the curve. So because we're going to want to compute something for different nearby points, I want to take a general point, x. And if I want a point on the curve, well, when my x coordinate is x, if my curve is y equals x squared, then my y-coordinate has to be x squared, right? If my x-coordinate is x and I lie on the curve y equals x squared, then my y-coordinate has to be x squared. So I take a nearby point on the curve q, and then we find the slope of the line from P to Q. So remember we said that we can calculate that by doing change in y divided by change in x. So the slope of the line from P to Q is just change in y divided by change in x. So we have change in y is x squared minus 4 divided by change in x, which is x minus 2. Okay, so the slope of the line from P to Q is x squared minus 4 over x minus 2. Okay, and then we want to compute that for different points Q as Q gets closer and closer to P. Okay, so what do I mean? So P is 2, 4, so Q will get closer to P when X gets closer and closer to 2. So here are some different values of X we could use and different slopes we could get. For instance, if you plug in X equals 3 into this formula for MPQ, you will get X squared minus 4 will be 5, and then X minus 2 will be 1, so we get 5 divided by 2, which will be 5. And then, okay, you can substitute in some other values of X and see what you get. So this was step 2. And then step 3 said the slope of the tangent line is the limit or the value, the slopes of the second line's approach as Q approaches P. So we have to look at what happens here as X approaches 2. And if we look at what happens as X approaches 2, well, as we go from the right, we're getting very, very close to 4 from above. And as we go to 2 from the left, we're getting very, very close to 4 from below. So either side, as X is getting close to 2, the slope is getting closer and closer to 4. Okay, so in this case, as X approaches 2, the slopes of the lines PQ approaches 4. So the slope of the tangent line is going to be 4, right? We have to look at what they approach, they approach 4. Okay, so now we know the slope of the tangent line. We can use point slope form. We know the tangent line passes through P, which is 2, 4. We know it has slope 4. So point slope form, y minus 4 equals 4x minus 2, right? Y minus y1 equals mx minus x1. And then you could expand and rearrange if you like to write it in the form y equals mx plus b. So we managed to find the slope of our tangent line in this simple example. Okay, so there are two things to notice. So the first thing to notice is that the slopes of the second lines, the slopes of the lines PQ, give better and better approximations of the slope of the tangent line as Q gets closer and closer to P. So it's not just enough to pick, Q, one value of Q or one point Q and find that slope. We have to look at what happens, what is the pattern as Q gets closer and closer to P. So in this table, we saw the pattern, right? The slopes go closer and closer to 4. Okay, and the second thing to notice is it does not make sense just to plug in, right? Why do we have to look at what happens as X approaches 2 rather than just plugging into? So there are two explanations. One, if I want to think about this algebraically, the slope PQ was X squared minus 4 divided by X minus 2. If I just try to plug in X equals 2, rather than looking at the pattern as X approaches 2, if I just try to plug in, I'm going to get 0 on the top and I'm going to get 0 on the bottom. I would get 0 over 0. Okay, that's bad news. I can't make any sense of it. So algebraically, it doesn't make any sense to plug in. But also, if we think about conceptually, so the steps were we were finding slopes of lines from P to Q. If I let Q equal P, then I can't find the slope of the line from P to P, right? P is just the point. If I start at P and I go to P, I don't go anywhere. I don't have a line, so I can't find any kind of slope. Okay, so I cannot just plug in this case. We really need these things called limits, where we look at the pattern as our input approaches some number, but is not necessarily equal to it. Okay, so this was just a kind of first motivating problem for why we have to study limits. In the next video, we're going to see another problem, and then in the next section, we'll actually get onto studying limits. And I stole a few pictures from Wikipedia, so I should attribute them. Here are the places, so thank you to the people for the pictures. Okay, that's all for today, and let's move on to the next video. Thank you, bye-bye.